Now, if you get the chance, it's always worth having a look around the various cupboards in the physics labs. This is something that me and the technician found recently. We don't know how old it is. I suspect it's probably something from before the Second World War. And what it is you take this thing out and you put it in here. And this is effectively a two-pole switch. So you can basically have this connected to the one part of the circuit, and you can either send the electricity this way, or you can undo that part and then send the electricity the other way. And this is the key thing in a circuit that you can use to look at how capacitors discharge and charge up. Also in the cupboard, I found one of these, which is just a thing that you can basically connect up as your capacitor, and then you can change, as you kind of turn the dial, from different sorts of capacitances. Now the key thing is that capacitors tend to have a really, really small capacitance measured in farads, and this is often paired up with a resistor with quite a high resistance. Now for this experiment, the kind of capacitors that you tend to use are electrolytic. That means you need to make sure that you connect them up the correct way in the circuit so they don't blow up, although I've never actually seen them blow up myself. This one here is 1,000 microfarads, and what we can then do is mount it in a component holder, or perhaps sometimes you get them already sort of pre-wired in to a box, a bit like this. You also need a resistor, and the resistors tend to be in the range of sort of 10 kilo ohms to 100 kilo ohms. And these are set up in a circuit that looks a bit like this. So you have some kind of power source here, you've got your capacitor, which is down here. You then also have a resistor, which is over here. And when you switch the switch from one side to the other, effectively what you do is you take this fully charged capacitor, you discharge it through the resistor, and then you can measure the potential difference using a voltmeter or some kind of multimeter. And what this is about, there's two ways of doing it. You can either set up to a data logger to record your potential difference and how this changes with time. The other way to do it is you can do it manually. And so when you do it manually, you start the timer, and what you can then do is record the potential difference at maybe every 5-second or 10-second intervals. And this is something which is really hard to do, trying to keep an eye on the time and actually record this at the same time as well. So there's ways that you can get around it. You might work in pairs perhaps, where one person is calling out the time every 5 or 10 seconds, the other person is taking the reading off the voltmeter. The other way you can do it is to video it, maybe using your phone, and then you can play back and actually get your exact time. So if you put the two things next to each other, when this gets exactly to 30.00, you'd have your exact reading. So you can take your readings of time maybe at 5 or 10 second intervals as this thing discharges. You can look at the potential difference that you read on that voltmeter, and then what you can do is take the natural log of ln V also in volts, okay? We can then do, or what you should be able to do, is you can plot a graph with T on the x-axis and ln V on the y-axis. And because the potential difference decreases over time and you kind of take the natural log of that, what you'll get is a graph that should look a bit like this. So why is that? Well, if we think about the equation to do with capacitors, where V is equal to V naught e to the minus T over RC, if you take the natural log of both sides, we can say that ln V is equal to ln V naught minus T over RC. We can write the same equation, just rearrange it to say that ln V equals minus 1 over RC times T plus ln V. And now we can see this is in the form of Y is equal to mx plus C, where the Y term is ln V, the X term is T, and that means that the gradient M is equal to minus 1 over RC. And it also means that the intercept over here is equal to ln V naught. So there's different variations that you can do. You can maybe find an unknown value of a resistor perhaps, or just check the capacitance of your capacitor, maybe find out the original potential difference that it was charged to. There's loads of different variations when you actually do this in class, but hopefully with this basic circuit, with this data and this graph here, that will really help you when you do this practical work.